Hi, Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon to all the viewers of distinguished lecture series. My name Nohasro Akmal bin Ganiman, and today is my utmost pleasure to invite Professor Dr. Byung Sun Kim together with us in 93rd Distinguished Lecture Series, Faculty of Engineering, University Technology Malaysia. For your information, Professor Kim is my supervisor during I became guest researcher in Korean Institute of Material Science. We working together to develop novel nanocomposite for aerospace application. Besides, as a supervisor, he also like my father there, which always helped me to adapt with the environment in Changwon, South Korea. Professor Kim is a very committed and helpful person and also have a good collaboration with University Technology Malaysia, especially with a School of Mechanical Engineering. Professor Kim always give his fully support to the collaboration or any event organized by our school and faculty. And today, we are so grateful to have him in our distinguished lecture series with interesting topic with title Electrophoretic Deposition Process and Nanocomposite. With his wide experience in composite field, I believe that his session today will give a good impact and open our eyes in the advancement of composite and research area. Okay, viewers, without further ado, I would like to pass this session to our Dean, Professor Dato' Muhammad Rafiq, to roll the ball on together with Professor Byung Sun Kim. You are welcome, Prof.
Dr. Hasrul, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Welcome everyone to our 93rd UTM Engineering Distinguished Lecture Series. My name is Muhammad Rafiq and I am the Dean of Engineering, University Technology Malaysia. Today it is my utmost pleasure to welcome Professor Byung Sun Kim from Korea Institute of Materials. A bit about our distinguished speaker today. Dr. Byung Sun Kim has been a researcher at the Composites Research Division (CRD) of Korea Institute of Materials Science since 1991. He was a professor in Advanced Materials Department, Korea University of Science and Technology (UST) from 2012 until 2017, and also was NSF appointed professor in Mechanical Engineering, Changwon National University between 2015 and 2017. Between 2010 and 2016, he was a director of Weekly Research Lab at between PCM of University of Delaware and CRC of KIMS on advanced hybrid micro nanocomposites for structural and multifunctional applications. He received his Ph.D. from the Department of Mechanical and Aerospace Engineering from Missouri University of Science and Technology, USA. Between the year 2000 and 2007, he was director of KIMM-MIT, Massachusetts Institute of Technology, Collaborative Program, and visiting professor at MIT between the year 2000 and 2002. In 2007, he was awarded the Korean Presidential Commendation for excellence in research into the structural design and processing of composite materials. He was the president of the Korean Society for Composite Materials from 2012 to 2013 and was an executive council member of International Committee on Composite Materials (ICCM) from 2013 to 2015. So that is a brief biography of our distinguished speaker today. Here now is Professor Byung Sun Kim from Korea Institute of Material Science with a lecture entitled In Electrophoretic Deposition Process and Nanocomposites. Professor Byung Sun Kim, over to you.
Hi. Good afternoon, and thank you for such a nice introduction, Professor Rafiq and Professor Hasrul. Thanks for inviting me to the distinguished lecture series at UTM. Well, instead of going on and on with my background, maybe I should just share screen and start. Can you see the screen?
Not yet, Prof. Have you shared your? Have you clicked the
Can you
share
see
screen button?
the? Can, okay, let me. No. I'm not successful with the sharing.
What is the message on your screen when you click the share screen button?
It worked before and now it's not.
What does it say?
In the application program window, I don't see any.
Have you opened your PowerPoint file, PPT file? Okay, we see something. Oh,
Okay, let me try again.
you need to open the PPT file first before you share screen.
So I go share screen,
Yep.
and I don't see my PPT file on the screen.
Have you opened your PPT file?
Yes.
Okay. Can you try your entire screen? There are
Hmm?
two. One is application window. The other one is entire screen. Can you try click on the entire screen?
One in the middle.
The one, the first tab. Okay, we got something. Excellent. And then you can go to your PowerPoint file.
Can you
And
see
open.
it? Can you see?
Yes. We can see StreamYard actually. Have you opened your PowerPoint?
Yes, I did. Can you see my PowerPoint?
Nope. Did you click application window or entire screen?
Okay, let me retry.
Yes, that's right.
Okay. So I click on the share screen
That's right. And then there
and
will be
share
a pop-up.
screen again. Okay, I'll share screen again. And I only see, I only have one choice, whole screen, application screen,
Window.
and then I don't see anything.
Oh, right.
Let me leave the studio and come back again.
Or okay, let's try and do that.
Okay, I will leave the screen and come back.
All right, okay. All right. Hasrul, in the meantime,
Yeah.
you would like to say something about your collaboration with Prof. Kim?
Yeah, our collaboration with Prof. Kim start on 2014. Before that, Professor Kim also, we invite Professor Kim as a keynote speaker in several conference organized by, at the time, Faculty of Mechanical Engineering. And on 2014, I go there as a guest researcher to the Changwon, South Korea. Changwon is at Busan, 1 hour from Busan, South Korea. And so we are working together in development of a novel nanocomposite for the aerospace application. Okay, I can see that Prof. Kim already there. Hi, Prof. So you already opened your PowerPoint slide?
I'm in, but I still cannot open my PowerPoint.
Oh, okay.
I opened my PowerPoint, but you cannot see mine.
Yeah, okay. Maybe you can click on the share screen.
Oh boy. Uh, I did, and
Okay, share
somehow
screen. Or maybe, Prof, you can email to us your PowerPoint slide, then I can click share screen.
I cannot hear you. Oh boy.
Okay, Prof, maybe you can just email to me your PowerPoint slide.
I don't know if I can do it that fast. Okay.
And CC to me.
I am emailing my PPT to you now.
All right.
Okay.
Okay. And to me as well, Prof. Yeah.
No, to Hazrul.
Okay, no problem, Prof. I'm waiting for the email.
While waiting for the email, is it possible, Prof. Kim, to try again one time?
Send one more time.
No, try and share the screen one time because we sent the email already. So Hasrul is waiting for the email. While waiting for the email, is it possible for you to try
Yeah,
and
email
share?
is still going.
Yeah.
Email is still going.
Right, right. While waiting for the email,
Yeah, okay.
is it possible for you to try and share your screen? When you click share screen, what kind of pop-up window do you get?
Uh, it says whole screen, application program window, micro edge tab. But
Oh,
uh,
are you using Microsoft Edge, Prof?
no, no, I'm
Because StreamYard works best with Google Chrome.
okay. Let's see this team yard.
Yeah.
Yeah, so if you're using Microsoft Edge, then StreamYard is not supported.
I'm
Okay.
waiting for the email, Prof.
Do you have Google Chrome, Prof?
Yes, I do. I think Hasro should have received my email.
Not yet, Prof.
No, brother.
Oh, okay. There is something. But,
Oh,
but it is on display right now. But can you find your PowerPoint?
Did you get my PowerPoint?
not yet, Prof. I keep refreshing. Okay, just received.
Okay, good.
Okay, I'm sharing screen now. Okay.
Yeah. Okay. Okay, let's go to next page. Okay. Uh, in the presentation, I would like to discuss the followings. What is nanocomposites? Why multifunctional nanocomposites? How to process hybrid nanocomposites? What is electrophoretic deposition process? How to fabricate carbon nanomaterials-based hybrid composites? What is nanocomposites? When a polymer is reinforced with nano-sized filler, such as clay or carbon nanotubes or graphene, the resulting material is called nanocomposites. At least one dimension of the filler should be less than 100 nanometers. Polymer nanocomposites are multi-phase hybrid materials that shows significantly better thermal, mechanical, barrier, and flammability properties in comparison to the base polymer at relatively low filler loading. Due to its ability to offer uh, enhanced properties, polymer nanocomposites seeks is placed in most of our commodity products today. Next page, please. Why multifunctional nanocomposites? Due to the development of aerospace, energy, electronics, the telecommunication industries, several requirements are combined in composite systems. Current efforts are focused on improving mechanical, electrical, and thermal properties, as well as combining health monitoring systems with structural composite. Presently, composite materials provide outstanding properties, however, relatively simple functions. The future may require higher-end multifunctionality, including hybrid, light and compact, higher integration and eco-friendly. Future may also demand structural functional, multi-scale, hybrid and intellectual and smart composite. Multi-scale hybrid composites are the materials that makes use of nanofillers to improve the mechanical properties of conventional fiber composites, such as interlaminar shear strength, or to incorporate new features on them, such as electrical properties. Multi-scale hybrid composite requires the development of technologies for the advanced carbon nanoparticles, microfiber, multi-scale, multi-directional hybrid composites with structural performance and multifunctionality. Multi-scale, multi-phenomena modeling of a structure, property, function requires modeling hierarchy, bridging the scale from nano to micro. Advanced micro-nanocomposites is the combination of the reinforcements with different length scales. It simply is an addition of microfibers and carbon nanomaterials. Microfibers provide structural properties such as light and strong, easy tailoring, and design flexibility, while nanomaterials may provide ultra-high strength, high functionality, and high aspect ratio. The addition of these two materials are micro-nano hybrid composites, which may have improved mechanical properties, good functional properties, multifunctionality, tailoring, and design flexibility. Moreover, if conductive metal particles are additionally introduced to nanocomposite, further increase in electrical conductivity and the mechanically stronger network may be added. In processing of hybrid composites, the bottleneck technologies are difficulties of even dispersion of nanoparticles within the matrix, which causes particle agglomeration, difficulty to infuse nanoparticles into the preform due to high viscosity. Overall, limited percentage of nanoparticles and the lack of uniformity within the composite may occur. Overall, this phenomenon can be seen in the top view. When the CNT and the resin mixture is poured to a stack of fabrics, the CNT may be poorly dispersed and agglomerated at the area of CNT addition. The bottleneck technologies are responsible for the reduction of structural and functional properties of the hybrid composite. However, with improved technology, these issues may be solved. With new technologies, high percentage of carbon nanomaterials and uniform distribution can be achieved. By hybridization of the reinforcements, carbon nanomaterials, even deposition on carbon fabric by EPD may be processed. By hybridization of carbon nanomaterials and resin, B-stage resin film may be processed. In the bottom left view, the resin is added to a stack of carbon fabric with evenly deposited CNT before the hybrid composite processing. And in the right view, the resin film containing evenly distributed CNT by calendering is alternatively stacked with carbon fabric before processing with resin film infusion process. This slide summarizes some of the previous researches on hybrid composites. Top left is CNT aluminum composite processed by hot press and extrusion. Bottom left is CNT aluminum composite processed by spark plasma sintering. Top right is CNT copper composite processed by molecular level mixing. All these three processes have used mechanical mixing techniques and high sintering temperatures. The results were inhomogeneous nanoparticle dispersion and the composite degradation and also slow process and low scalability. However, with EPD process, simple and effective dispersion may be achieved, and the final composite is readily scalable for large scale production. Van der Waals forces include attraction and repulsions between atoms, molecules, and the surface, as well as other intermolecular forces. CNT is known to possess very high aspect ratio of about 10,000, Young's modulus of 1 to 2 terapascal, and the tensile strength of 200 gigapascal. However, due to Van der Waals forces acting between CNTs, the bundling and poor dispersion of CNT exists within the matrix, which as a result causes poor wettability within the matrix. And these are the major obstacles for the most efficient composite applications. The electrophoretic deposition process is based on the movement and the deposition of charged particles on the electric field onto a conductive electrode to develop thin or thick films and the coatings. The advantage of EPD process are the short formation time, simple apparatus, the ability to produce uniform coatings on complex geometries. In other words, electrophoretic deposition is electrocoating method such that the charged particles in a suitable suspension move toward an anode or cathode under the electric field. Aqueous suspension is used in this method. Under the electric field, the charged particles in the solution are moved and deposited on the opposite electrode surface. Next. Next page. Okay, thank you. In manufacturing of novel CNT copper hybrid, there are two ways to treat carbon nanomaterials, such as CNT. In cathodic EPD process, as shown on top portion of this flow diagram, CNTs are PEI treated to have plus charge. Then these CNTs via EPD process will be deposited on the surface of the carbon fabric to produce formicary-like CNT copper nanostructures. In anodic EPD process, CNTs are hydrochloric acid treated to have minus charge. Then these CNTs via EPD process will be deposited on the surface of copper-coated carbon fabric to produce CNT copper nanoplatelets. In next few slides, the EPD processes will be discussed in more detail. In cathodic EPD, under an electric field, there will be electrical oxidation on anode. Then the copper element from the copper plate and the plus charged CNTs move toward the cathode and are simultaneously deposited on the surface of the carbon fabric. The picture of the copper plates below show dark copper plate before and the cleaner copper plate after the cathodic EPD process. Well, this method may be used to clean copper plate, although it may be a little bit expensive method. Cathodic electrophoretic deposition process has been applied to produce unique carbon nanotube copper nanostructures on the carbon fiber surfaces. During the deposition process, ionized copper and positively charged CNTs are accelerated towards the carbon fiber on the applied electric fields. An interconnected formicary-like network of nanotubes and the nanoparticles is formed where the copper nucleation and the growth occurs predominantly at the nanotube crossings and edge contact locations. When embedded in a structural composite, the CNT copper structures create a highly conductive and strongly bonded network shown by the significant enhancement in both electrical conductivity and the interlaminar shear strength as compared to composite without the CNT copper nanostructures. Therefore, the electrical conductivity of the hybrid composite in all directions may be same and outstanding. Anodic EPD is two-step deposition process, which are thermal vapor deposition of copper on carbon fabric before anodic EPD process. Thermal vapor deposition of copper on carbon fabric is the sputtering of copper element on carbon fabric. In anodic EPD process, under an electric field, minus charged CNTs move toward an anode and are deposited on copper-coated carbon fabric. The schematic drawing below shows carbon fabric before and after copper coating by thermal evaporation. Obviously, brown color is clearly the copper element deposition. Carbon nanotube reinforced copper nanoplatelets were developed by simple two-step deposition method. They are thermal vapor deposition of copper and anodic electrophoretic deposition of CNT. Due to the fast corrosion during the electrophoresis, the copper layer is broken into pieces and exfoliated to form a platelet structures. Then during the EPD process, the CNT deposition will bridge the gaps. Consequently, highly conductive and strong CNT copper nanoplatelets are effectively built up. When applied in carbon fiber composite, the CNT copper nanoplatelets significantly enhanced both interlaminar shear strength and the electrical conductivity comparing to baseline composites. In nanocomposite fabrication and characterization, 6 plies of carbon fabrics are EPD processed at the same time. Aqueous solution is used in the process. The processed carbon fabrics are dried and vacuum-assisted resin transfer molding processed to produce test specimens. The electrical conductivity tests are carried out for copper CNT and the carbon fabric network in plane and through the thickness of the nanocomposites. Mechanical tests are performed for shear stress and short beam properties of the nanocomposites. The graph represents the electrical conductivities for various nanocomposites. The nanocomposites are by copper only by cathodic process, copper only by thermal process, CNT only by anodic process, CNT copper formicary, and CNT copper platelets. The in-plane electrical conductivities for all nanocomposites appear to have fairly similar values. However, the out-of-plane electrical conductivity is the highest with CNT copper formicary nanocomposite, and the CNT copper platelets nanocomposites show almost as good values. The graph represents the interlaminar shear strength for various nanocomposites. Among all, the interlaminar shear strength is highest with both CNT copper formicary and the CNT copper platelet nanocomposites. This may be due to the higher deposition of copper at CNT interfaces for CNT copper formicary nanocomposite and that of CNTs in the gaps between carbon fiber and the copper layers for CNT copper platelets. This is a morphology for the fracture surfaces of nanocomposites compared with microcomposite. The fracture surface of nanocomposite is quite smooth compared with that of all nanocomposites. Fracture surfaces of all nanocomposites show deposition traces of CNT as well as copper. However, bottom three are showing more depositions of CNT and copper respectively. CNT copper depositions are seen on the fracture surfaces of formicary and the platelet nanocomposites, while only CNT is deposited on CNT-only nanocomposites. These fracture surfaces may explain that the bottom three composites' electrical conductivity and the interlaminar shear strength have relatively higher values. Using the sizing agent characteristics of graphene oxide, the electrophoretic deposition process is used. In this process, when the electric field is applied to substrate in the graphene oxide solution, graphene oxide can be attached to the anode substrate because graphene oxide has negative charge. So here, the carbon fabric is connected to the anode and the stainless steel to the cathode as the counter electrode. When the electric field is applied, graphene oxide is coated on the carbon fabric surface. And finally, graphene oxide coated carbon fabric reinforced composite is dried and stacked to be fabricated using VARTM process. As shown in the same morphologies, graphene oxide are very well coated on the carbon fiber surface with 7/10,000 and 7/100th of a weight % of the graphene oxide, respectively. Here, the interfacial property of graphene oxide coated carbon fiber is investigated in terms of both quantitative and qualitative approaches. When micro drop of epoxy resin is on a single carbon fiber, graphene oxide coated carbon fiber showed less contact angle, which means the graphene oxide increased the wettability with epoxy resin. And also, when the surface free energy is calculated by equation shown here, which is the sum of dispersive and the polar components, graphene oxide coated carbon fiber showed higher polar and dispersed surface energy. Therefore, it can be proved that the interfacial strength, between carbon fiber and epoxy is higher. The graph shows the effect of graphene oxide coating on the interlaminar shear strength. Interlaminar shear strength is an important material property for the design of laminated composite structures subjected to transverse load. Only with 7/10,000 of a weight % of graphene oxide coating, the interlaminar shear strength is increased by almost 10%. Previously, same results was obtained with more than 1 weight % of carbon nanotubes. Same morphologies on the fracture surfaces of carbon fabric on top and graphene coated carbon fabric composites are shown at the bottom. In carbon fabric composite on top, it can be seen that the cracks have propagated following the resin-rich interface between the fabric and the matrix. In graphene oxide coated carbon fabric composite shown at the bottom, the cracks have propagated through the thickness, explaining the improvement in the short beam strength. In the next few slides, wire-type multifunctional hybrid composite fibers are discussed. As for the wire-type supercapacitor, the requirements for the wire-type supercapacitor are that the stretchable wire type supercapacitor for wearable device, which should have high electrical conductivity, flexibility, high specific surface area, and tough stretchability. Carbon fibers may be used as the collector for supercapacitors since it has high electrical conductivity and high flexibility. However, carbon fibers have a poor surface area, which is only 5 meters squares per gram. And this needs to be increased since the performance of the supercapacitor is dependent on the specific surface area. In order to increase specific surface area, our strategy was to decorate the single-wall CNT aerogels, which have the largest surface area and good electrical conductivity around the carbon fiber surface. Firstly, graphene-coated single-wall CNT aerogel was synthesized as shown in the photos. We carried out the in situ polymerization of dopamine around the single-wall CNT network as shown on top schematic drawings. Uniform coating of graphitic layers were achieved with carbonization and nitrogen-containing graphene. Graphene-coated single-wall CNT aerogels are mechanically stable even after the water absorption. Three-dimensional carbon nanostructure hydrogel was coated around the carbon nanofibers, which is core collector. Increased surface area and capacitance for wire-typed electrodes via porous SWCNT networks are obtained. Graphitic layers coating on the single-wall CNT networks is established, which enhanced in mechanical and electrical stability of porous structures, which possesses low equivalent series resistance and high electrical double layer capacitance. Wire type supercapacitors by combination of two electrodes are tested to use as a device. As a result, low IR drop and low ESR was obtained, which showed good interface between carbon fiber and the single-wall CNT networks. Stable electrical double-layer capacitance performance was obtained that is parallel to imaginary impedance axis at low frequency. Low ion diffusion and transfer resistance was obtained, which is low Warburg impedance. Stable capacitance performance was seen under high current density, which is 64% retention. Elastomer polyurethane wire and helical wire type supercapacitor was designed as shown on top left with stretchable wire type supercapacitor. After removing polyurethane wire, stable capacitance at high tensile strain was obtained with 7.5 reduction at 100% tensile strain. Stable cyclic capacitance was obtained with 10,000 cycles of tension from 0 to 50% strain and 94% retention. In Ragon plot, our wires power density is indicated by red and blue stars and could provide higher energy and power density compared to the commercial capacitors. Comparable performance to the graphene-based film type supercapacitors, high performance compared to other wire type electrical double layer capacitances. Can I continue or should I stop because of the time? Okay, I go on. In order to have improved fiber type transistors with higher electrical conductivity, stronger mechanical properties, and higher flexibility, graphene fibers are manufactured. In wet spinning of graphene fibers, the aqueous graphene oxide suspension was loaded in a plastic syringe and injected into the rotating coagulation bath of hexadecyl trimethyl ammonium bromide solution. In the wet drawing of the graphene fiber, the wet drawing system was simply realized in the drawing process by adjusting the distance between each end of the gel fibers. Next, please. In the hybridization of silver nanoparticles, in order to apply graphene oxide fiber as a highly conductive, mechanically strong, and flexible electrodes for the fiber type transistors, a silver precursor was introduced in graphene fibers and then converted into silver nanoparticles. Next page, please. In hybridization of silver nanoparticles, SAM and the energy dispersed spectroscopy mapping images of the graphene silver hybrid fibers show that the silver nanoparticles of about 100 to 200 nanometers in diameter have completely covered the fiber surface, forming a continuous silver shell and got settled in the interior of the fibers. Next slide, please. In the characterization of the silver graphene hybrid fibers, the bending test of the hybrid fibers are carried out. Bendability of the hybrid fibers with low draw ratio was superior to that of the flat hybrid fibers with high draw ratio. The resistance of the hybrid fibers with 1 and 1.2 draw ratio showed an abrupt increase at the bending radius of 1.5 millimeters, where the fiber with 0.6 draw ratio exhibited no differences in resistance at 1 millimeter radius. We'll skip this slide and go to the conclusions, please. As for the conclusions, fabrications and the possible applications are discussed for the multi-scale hybrid composite reinforced with carbon nanomaterials, polymer composite reinforced with preform porous single-one CNT architecture, and the wire-type hybrid composites. Thank you. Any questions?
All right. Thank you. Thank you, Prof, from the presentation. So now we open to the floor. If any question for the viewers, if you have any questions, you can drop at the comment below on the Facebook Live. Okay, if no question, I have a question for you, Prof. Okay, Prof. Okay, we have one question from Dr. Nur Akmal Fadil. Okay, Dr. Akmal said in preparing hybrid fiber, the nanoparticle was synthesized during the coating for hybridization, or the nanoparticle was prepared earlier? Prof, what your comment on this?
Yeah, okay. Yes, nanoparticles were prepared earlier because when you are going through synthesization, you cannot prepare and synthesize at the same time. They have to be performed separately.
All right. Okay. I hope the answer given by Prof is okay, Dr. Akmal. Okay, Prof. The other question, when you coating with the carbon nanotube, when you increase the percentage of carbon nanotube, why the interlaminar shear strength is going down?
Okay. If you have, instead of carbon nanotube, if you have a carbon nanofibers, then the carbon nanofibers can, well, their aspect ratios are much larger than that of CNT and a little flexible as well. So they can link the each layers of the fabric. Then they can improve the mechanical strength. However, when it is a CNT, they are short and stiff, not flexible. So if you have too much, they act as impurities in between the layers.
I see. All right. Okay. Thank you, Prof. The other question, from your opinion, what's the future trend of the supercapacitor? Where is the application for the supercapacitor?
Okay. Would you go to next slide?
Okay.
Well, I cannot see it. Can you?
Oh, okay.
Put
Wait.
it?
Okay. Okay. Can you see that?
No, I can't.
Oh,
Because
okay.
after the thank you slide, go to next slide of the one I gave you.
This one? Oh,
okay. Supercapacitors, they are used to store or release huge amount of energy in very short time. So supercapacitors can be used in hybrid electric vehicle, or fuel cell vehicle. And transistors, they can be used as electric switches in digital circuits. And finally, electromagnetic wave, the nanocomposites can be used as electromagnetic wave shield and absorption. So for example, cellular phones, 10, 15 years ago, you talk too much on the phone used to get warm.
Okay.
And because at the time the nanoparticles were too expensive to put in your cell phone, but now it's much cheaper, so they put more in your cell phone cases, and you talk as much, and your phone doesn't get as warmer as before.
Okay.
That's because the electromagnetic waves are absorbed.
I see. All right. Okay, Prof. We have another question from the floor from Dr. Jamari Ghaffar. Hi, Prof. How about the cost in fabrication of hybrid composite compared with traditional CFRP? In example, aerostructure product for strength and weight.
Well, right now it's more expensive because what I've shown you is the lab scale work. So, well, if we come up with some processing equipment for large scale productions, maybe it can be comparable. But at this moment, we only did it in a lab scale, so I would say more expensive.
More expensive. All right. Okay, Prof. So I think there is no other question from the floor. So I think that's all for our session today. Thank you, Prof, for the very fruitful sharing and great presentation. So I hope we can, after all the benefits in the Changwon again.
Okay, no problem. It's been
All
my
right.
pleasure of talking. I'm sorry about the little bit mess at the beginning.
No problem. No problem on that. All right. Okay. Thank you, Prof, for the sharing. Thank you for your time today. We are from Faculty of Engineering, University Technology Malaysia. Really appreciate your time and your presentation as well as your sharing today. Okay. For the others, thank you for watching this live distinguished lecture series, and see you on the next distinguished lecture series. Thank you. Bye. Assalamualaikum.
Bye-bye.
Bye.